Welcome to the Health AI Brief, breaking down the AI shaping our world one concept at a time. So the end result of training an AI is what we call the model. This is the finished product that does the actual predictive work. But this then leads to the next logical question: what does that engine, the model itself, actually look like? When a machine learns from data to make clinical predictions, how does it work? So there's a lot of different types of machine learning, which we'll come to in more detail in later episodes, but the structure behind most of the biggest advancements in modern machine learning are named neural networks. And this name's intentional. Just as our own biological neural networks underpin human intelligence, these artificial networks operate on a similar, albeit vastly simplified, principle of interconnected nodes processing information. The best way to understand it is to think of a logical chain for synthesizing information, just as we do during a clinical workup. So let's take a patient with chest pain. We're flooded with information. At the start, you have an input layer. This is the entry point for everything: the raw electrical signals from an ECG lead, the chemical makeup of a blood sample, the patient's age, their risk factors. It's a torrent of raw data coming into this input layer of the neural network. This data is then fed forward into what are called hidden layers, which are like a series of processing stations. A set of nodes, or they sometimes called neurons, in the first hidden layer might act upon the ECG machine itself, taking the raw electrical signals and transforming them into recognizable patterns like ST elevation patterns. Another set acts like a lab analyzer, turning the raw blood data into something like a troponin level. And the crucial part is that the next hidden layer doesn't see the raw data, it only sees the processed output from the first layer. So a neuron here might learn a new, more abstract rule, like if ST elevation signal is strong and there's raised troponin signal is also strong, then send a more powerful kind of high risk signal up the chain to the next level. And then after processing in all of these hidden layers, we finally reach the output layer, which takes all of these highly refined concepts from the last hidden layer and makes the final simple call we need: cardiac chest pain or non-cardiac chest pain, or kind of that's what makes the prediction. So how does it learn? So during training, if the network gets a diagnosis wrong, feedback is sent back through the network in the other direction to adjust the weight or importance of each connection. It's a huge process of trial and error where the network learns that for chest pain, the troponin and the ECG inputs are critically important, while the connection for, say, the colour of the patient's big toe should be given an almost zero weighting. So if you make a big error and it makes a very big mistake, then that feedback signal will be stronger, indicating that bigger changes need to be made in the network. But if it's actually quite accurate, then you don't need to make quite so many changes in the network, and that feedback signal will be less strong. So kind of as you go through the network from the input layer through the hidden layers up to the output layer, you get kind of more detailed abstractions of the underlying data. So the input layer just takes the raw data, and that's gradually built upon to more complex abstracted representations of that data, all feeding into that output layer where the final decision's made. So what are the takeaways here? I think it will hopefully have been a helpful example to provide at this stage to understand a bit about how AI and particularly machine learning techniques process and interpret data. First, it shows that neural networks are powerful pattern finders, not biological reasoners like human intelligence. If by a statistical fluke most cardiac patients in the training data happen to have been admitted on a Tuesday, the network might learn to associate Tuesday with risk. It finds correlation, not necessarily causation. Second, this structure is what allows AI to handle the messy, complex, real-world data that we deal with every day. It can find subtle, non-linear relationships between dozens of inputs that a simple risk score can never capture. It's the basic architecture that allows a machine to move beyond fixed rules and start learning from clinical data and detecting really complex patterns within it. So that's neural networks in a nutshell. Not a brain, but a powerful and flexible architecture for finding patterns and the fundamental building block for most of the advanced AI in medicine today. If you found that useful, please hit subscribe or follow in your podcast app so you don't miss future episodes.